In this lesson, we'll cover inverse functions, and that is a function that switches the x values and y values of some given function. To explain what this means, let's use the function f of x is equal to 2x plus 1. So that's this thing here, and I have 3 points labeled on the graph. For starters, this one. This is the point, it looks like 2, 5, which makes sense for this function. If you put 2 in place of x, you get 5 back for y. This is the point 0, 1, and that makes sense too. If you put 0 into this function, you would get 1 back. And then the last one down here, it looks like, okay, that's negative 5, negative 9. And that makes sense for this function as well. If you put in negative 5, you'd get negative 9 back for y. So the inverse function is going to be the thing that switches these x and y values. So instead of having 2, 5 on this function, on the inverse what you'd have is 5, 2. So on the original function, 2 went to 5. On the inverse, 5 goes to 2. Same thing for this point, the point 0, 1. On the inverse, you'd have the point 1, 0. So instead of 0 going to 1, 1 goes to 0. And same thing for this last point here. On the inverse, you'd have negative 9, negative 5. So instead of negative 5 going to negative 9 goes back to negative 5. I'd like to introduce the notation for an inverse function. If f is our original function, the notation we will use for the inverse is f to the power of negative 1. And that's just read f inverse of x. So it's a notation only to indicate that we are talking about the inverse of this original equation. Using this notation, okay, the point 5 going to 2, on the inverse function, you'd say f inverse of 5 is 2. Likewise, for the point 1, 0, that is f inverse of 1 goes to 0. And for the last one down here, that would be f inverse of negative 9 goes to negative 5. So this is what we mean by an inverse function. You'll have some equation. You can pick any points that you'd like on it, and your inverse is going to reverse them. But the question is, well, what is the formula for it? How can you find it? In example 1, I'm going to outline a procedure that you can use to solve for the inverse function. So at the very end, we will have a formula that is f inverse of x is equal to. So we'll actually have an equation for it. So step 1 is take your function, and instead of writing f of x, replace it with the variable y. So like write y is equal to 2x plus 1. And the only reason for this is it's easier to do algebra with this symbol instead of writing this whole thing. Step 2 is if you want to interchange the x's and the y's, don't have it solve for y, instead solve for x. So step 2 will be solve for x. Easy to do for this function. We can subtract 1 from both sides. And then my last step is to divide by 2. And we've done it. We have y minus 1 over 2 is x. Now, there is this last step where, well, I don't want to use this symbol. I want to use this thing to represent my equation. So I'm going to replace this x with this entire symbol. And I'm also going to call this y and x. I'm going to relabel it. So we're going to relabel things like this. So instead of x, I have this f inverse of x, and this y is now written as an input x. But that's it. What this equation does is switch the x and the y values. Let's see if it actually worked. If you recall, these points were on the original function f, and we claimed that on the inverse, you'd have negative 9, negative 5, 1, 0, and 5, 2. Are these points on this equation? Let's start by checking this one here. Is in fact f inverse of negative 9 equal to negative 5? Let's see, if you put negative 9 in place of x, okay, we get negative 10 over 2, and it worked. The inverse evaluated at negative 9 is in fact negative 5, so that's good. Well, what about this point? If I put 1 into the function, will I get 0 back? Let's see. f inverse of 1 is 1 minus 1 over 2. That's 0 over 2, and that worked too. We get 0. The last one is, well, what's f inverse of 5? Should be 2. That's 5 minus 1 over 2. That's 4 over 2, and that's 2. So this process switched the x's and the y's, and I verified these 3 points in it, and they all match up. All right, for a little extra practice, let's find the inverse function for f of x is equal to x minus 4 cubed. So our goal is to write this as f inverse of x is equal to some equation. Step 1 is, well, instead of writing f of x, let's call it something easier to write, which is y. And then we have x minus 4 cubed. The goal is now to solve this equation for x. And to do that, I want to get rid of this cubed. And the operation that we can use is take the cube root of both sides. So let me just rewrite this so there's a little bit more space. But if you want to cancel a cubed, you can take the cube root of both sides, or equivalently, raise both sides to the 1/3 power. On the left, we have the cube root of y that cannot be simplified anymore, but on the right, if you take the cube root of something cubed, they cancel and you're left with x minus 4. The goal is to solve for x. You can now add 4 to both sides of your equation. And when we do that, we get the cube root of y, then plus 4 is equal to x. This technically is the formula for the inverse. However, I'm going to call x this entire symbol and replace this y with an x. My equation now becomes the cube root of x, then plus 4. It turns out that there are functions that do not have inverses, like this function here, x squared minus 3. It has no inverse on its natural domain of all real numbers. So what's the problem? What would go wrong here? And is there an easy way to determine if a function does or does not have an inverse? The problem is, I picked these 2 points. This is the point -3, 5. So let me write that down. And on the same horizontal line, you also have +3, 5. On the inverse, if you were to find it, it switches the x and the y values. So on your inverse, you would have 5, -3, as well as 5, +3. Both of these points would have to be on your inverse function, whatever it is. But the problem is if you plot these 2 points, 5, 3, and 5, -3, they lie on the same vertical line. This violates the definition of a function. So you're technically not allowed to write f inverse of x because you have one input, 5, going to 2 different outputs. So the issue is it's not a function. So you can't actually find one. It's impossible. The way you can notice this ahead of time is by thinking of, well, are there 2 points that lie on the same horizontal line? Because if there are, on the inverse, they would lie on the same vertical line, and that is an issue. So this is something called the horizontal line test. If you can find one horizontal line, so I chose, this one here, and that one horizontal line goes through the graph more than once, it means there is no inverse function. So I stated this here. So, I chose this one, but really, once you find one, and it can be anywhere, it's no good. Now, here's a horizontal line that doesn't go through the graph at all, but that doesn't matter. If you can find just one, that's enough to say there is no inverse function. The terminology that we'd use is we'd say this is not one-to-one, meaning, okay, well, here we have one y value, but it goes to 2 different x values. So if something is one-to-one, there is an inverse, but that did not happen here. In example 3, I'd like to find the inverse for this function provided that it exists, because it's possible that, well, maybe there is no inverse function. So here I have the graph of this function, and I'm going to ask the question of, does this thing pass the horizontal line test? That is, does every horizontal line go through the graph at most once? Or can we find one horizontal line that goes through the graph twice? So just by looking at this graph, it's definitely 1-to-1. So I'll just note that this is 1-to-1. Each y value corresponds to exactly one x value. So like here, this horizontal line, it only meets the graph here at this one x value. Or this horizontal line, it meets right about here and you only get 1. This thing is always increasing, and going in this direction it's decreasing, so each horizontal line is only going through the graph once. So it's 1-to-1, it passes the horizontal line test. Therefore, if you write the equation like this, you are able to solve for the inverse function. All right, let's do it. I guess my first step will be to subtract 4 from both sides of the equation. So we get y minus 4 is equal to the cube root of x plus 2. And then to solve for x, I think I'm going to cube both sides. If you cube a cube root, it cancels to give you just x plus 2. On the left, you have y minus 4 cubed. Now, you could cube this out, but I think it's just easier to leave it as this because we can easily solve for x. I'm going to subtract 2 from both sides of my equation. And what I'm left with is y minus 4 cubed minus 2 is equal to x. I can now express this as an inverse function. F inverse of x is equal to, so here this x became this entire symbol, and this y is what I'm going to call x. So that is, it's x minus 4 cubed minus 2. So just a couple of final thoughts on inverse functions. If you start with this function here and find its inverse, you would get this equation. But the same thing happens if you start with this equation and find the inverse, which would be this thing. They're actually inverses of each other. Second, I graph both of these functions. So here's f of x, and this is f inverse of x. It turns out that if you graph a function and its inverse together, it is symmetric in the xy plane about the line y is equal to x. So it's kind of nice. Like if you have a function and you find its inverse, you can actually graph them together. And if you see this type of symmetry, you can conclude that, okay, these two functions are in fact inverses of each other.